We're almost through this thing. We're almost got all of the skills that of all the skills you need to get through this class, you've got most of them, like really almost everything that you'll need to know. There's a couple more things that we'll learn on Wednesday and like one more thing next week, but they are not, compared to what you've done so far, those are relatively small skills. So take heart, we're almost through this thing. Okay, admin stuff. Exercise 10, the final exercise, is posted. I'm going to call it due December 7th. I'm not sure if I'm technically allowed to say it's due December 7th because that's after the end of classes, but so feel free to hand this in on, let's say officially it's due December 5th and you all get a 2-day extension. You'll see that there's 5 multiplace derivations, so that's what we're going to do today, multiplace derivations, and then 5 of what are called invalidities. And we'll start doing that on Wednesday. So feel free to try it beforehand, but it won't make any sense to you until you've had it explained. And one of the reasons why I wanted to make this December 7th is because if you get stuck on one of these invalidities, so the 2 remaining skills that we've got are invalidities and what's called expansions. And the invalidities can sometimes be very tricky. But if you learn how to do expansions, then you've got a kind of mechanical technique that will help you solve the invalidities. So if you get stuck on one of these, as of Wednesday, you'll technically have the skills to do them, but it takes a little bit of creativity and insight to solve them, unless you learn the thing that we'll learn on Monday, which is expansions, and that reduces the creativity and insight required. It's a somewhat more straightforward method. So give them a shot after Wednesday. If that doesn't work for you, just wait until Monday when we'll learn the final skill of the course, expansions, where that will be easier to solve these. Okay? Questions about that? Good, fairly routine, I hope. Yeah, course evaluations are open. Please fill these out. That would be great. We'd love to know. This is sort of like, there is a very standard course, but there are always variations. We want to know how this version of Logic 245 went. So let us know, please. And the window is now open to do so. And I got at least one email asking if there's going to be any Logic Labs after class is over. The answer is yes, and we'll keep an eye on Quarkus for announcements. We'll have announcements for when those sessions will be. So good? Good. Okay, I think that's all of our course business. Before we get into multiplace derivations, I want to just refresh your memory and maybe do one more thing on multiplace symbolization. So we're going to, just to refresh your memory, to do one example that we haven't done, let's do this thing. I've got this on, let's do this by hand kind of thing. Okay, so this is, once again, this is an ambiguous sentence, and let's do it both ways. So I do want you to be able to spot ambiguities in sentences, and it's very likely that I'll give you a question on the exam where I present a sentence like this to you and say, this is ambiguous, tell me both ways to symbolize it. Okay, so you can fool some of the people all of the time. Maybe it's better if we do kind of a natural language version of identifying the ambiguity first and then symbolize it both ways. So you can fool some of the people all of the time. And what we're doing is try to figure out which bit can be either generic or specific. Right? So there's 2 readings here. The scope can either make one of these things generic or it can make it specific. The hint is that if you're saying something about all, then there's no question of generic or specific. When you say all, you're just saying all. So it's not the all that is ambiguous here. All is always unambiguous. It's the other bit. Some, yeah, so some people. And what you're saying is, you could either be saying, and it's helpful to rephrase these things. So this is something that I'm going to strongly recommend you try when you're doing these symbolizations. It will likewise be helpful when you're doing invalidities to rephrase these in what you could call logic-ese, right? So it's just you're saying something that you know how to symbolize. So you can fool some of the people all the time. that could be something like for all people. Oh, man. OK. Let me get calibrated on writing this thing. So for all people, there is no, sorry. That's obviously incorrect because it was not for all people. For all times, or for some people. Oh, that's right. Whew. OK, Monday morning. Welcome, everybody. OK, so you can fool some of the people all the time. So at all times, there exists at least or a generic person. Is that right? That you can fool? Then you can fool them. Or at all times, or there exists at least some people that at all times you can fool them. So OK. So the difference between those two sentences is the scope of each quantifier, right? In the first one, I've said the universal has a wide scope. So for all of the times, there's at least a few people that you can fool at that time. In the second one, we said there exists at least one person, or at least there are some people, such that at all times you can fool those people. Yeah? And what makes it, in the first case, a generic person is that the universal gets wide scope. And what it makes it a specific person in the second one is that the existential gets wide scope. Yeah? OK, so let's do this one first. Let's try to symbolize this. So at all times, it's obviously a universal. So for all, oh yeah, and when we're symbolizing these things, it's always a good idea if you've got a multi-place predicate. So F2, you can fool A at, that should say B, but you can cope. So you can fool something at some time. So let's say that X is our person. Just decide beforehand what variables are going to become which objects, and Y is a time. And then this is going to be you can fool a person at a time. So we know that we're going to end up with the multi-place predicate F. You can fool this person at this time. Yeah? And then we just construct the rest of the sentence around that multi-place predicate. OK, so that'll be our procedure. So keeping in mind that X is going to be our person and Y is going to be our time, so that you get these in the right order mostly. So symbolizing this first one, at all times. So for all Y's, because Y is a time, for all times, that is HY, then there exists some person, because person is our X, such that, well, they're a person for one thing, and you can fool them at some time, XY. Close brackets, close brackets, close brackets. OK? So because the universal gets wide scope, we're talking about all times and generic people. And then if we wanted to symbolize it the other way, we just give this existential wide scope. Keeping in mind that you have to, if you're symbolizing the multi-place predicate in this way, in both cases, it's you're fooling people at times. You're never fooling times at people. So you want to keep it in this order, meaning if you want to say that there exists at least one person, you need to use X out front. So X is a person, GX. And for all times, we got if H is a time, then you can fool a person at that time. Close brackets, close brackets, close brackets. Yeah? Good? Okay, so that's basically just another example of what we did last time, right? We've got all this down. Okay, since you're all very comfortable with that, let's make it a little bit harder and do 2 multi-place predicates. Well, I know you don't want to, but we're going to anyway. Okay. Okay, so here we go. So every student went to a school in a country. Okay. Because there are 2 things, there are a bunch of different ways that this could be symbolized. There are at least 3 different ways that this is ambiguous in like a few different ways. So let's start off by just asking in what ways could this be ambiguous? So we know that every student is unambiguous. We're talking about every student. No matter what scope that takes, you're always talking about every student. It's only the existentials that can be unclear, that can be ambiguous. So a school, are we talking about every student going to a specific school or a generic school? And are we talking about a specific country or a generic country? Yeah? Okay. So let's just start symbolizing these things. Let's try it. Let's try it a few different ways. Once again, let's start by figuring out which variables we're going to make each object represent. So let's say A is a student. So let's call X our student. Let's call Y our country. And let's call Z our school. Okay? So we're going to construct these. So we've now got 2 multi-place predicates. We've got A went to B, and A is in B. We're going to construct them both according to the scheme so that everything lines up well. So A went to B. Some student went to a school. So B is going to be a student went to a school. Yeah? And D is A is in B. So D is our other multi-place predicate. And we're going to say the school is in a country. A is in B. We want to talk about schools being in countries. So far, so good? Okay, so now we know what our variables are going to end up being, and we know what our multi-place predicates are going to look like. And now we just have to build the rest of the quantifiers around that scheme. So I'm just going to start symbolizing ways, and we'll talk about the different meanings of them, if that's OK. So let's start with the one that jumps out at me. If I was going to symbolize this one some way, I'd say every student went to a school in a country. I would say for all x's, because x's are our students, if ax, then there exists some country, say C is a country, and there exists some school, Z is our schools, so EZ, and now we just add these 2 predicates in here. So B, XZ, and D, ZY. OK. Now we close the 1 bracket, 2 brackets, 3 brackets. OK. So what we've got here is the following. For all students, there's at least some place, some generic country, and some generic school that they went to. Neither of these are specific, because to be specific means you're outside of the scope of this universal, right? Outside the scope of a universal, you're a specific thing. Inside, you're a generic thing. They're both inside the scope of the universal, so they're both generic. And it wouldn't make a difference if we'd put this, there exists a Z, outside the scope of there exists a Y. That wouldn't have made a difference, because they're both still inside the scope of the universal. Yeah? Similarly, we could have put the dz, no, that's all going to be inside here. The z's are in both. Okay, so that's good. Good? Okay, another one. So what if we wanted to say that they went to a specific school? A specific school. What do? You just put the quantifier that binds the variable that's going to be the school out front. You give it the widest scope. So you say, there exists some z, and z is going to be our school, ez, and if we want to say they went to a specific school in a generic country, it's weird, but we could say that. Then for all students, if A is an X, then there exists some Y such that Y is a country, and then our multi-place predicates. And we don't have to think too hard about these how to organize these multi-place predicates because we made those decisions right off the bat, right? We made those decisions here when we decided what variable is going to go with what kind of objects. So this is going to be common throughout all of our different, if you've got a bunch of ambiguous ones, those multi-place predicates are just going to be the same across all of them. Okay. And there's at least one more that we can do here. There's at least one more way of symbolizing this. So we could say there exists some, you could even put the y out front this time. There exists some country such that, and there exists some school. E is a school. And for all students, they went to that school. B, X, Z, and D, Z, Y. 4. Okay, now we're saying something about a specific country and a specific school that every single student in the universe went to that specific school in that specific country. Good? Questions? Yeah?
Every extension inside the scope of a universal quantifier means it's generic, and if it's outside, it means specific.
That's right. That's right. And it defaults, an existential defaults to the specific reading. So if you say there exists an X such that blank, what you mean is that there's at least one thing that's blank. It's only when it's inside the universal that it becomes a generic thing. So yeah, you got it. Okay? More questions about that? Or otherwise I'm going to move on. Yeah? Okay. So when we started, we were just talking about existential quantifiers, way back in like single place predicate logic, right? We're just like, there exists a thing. And then what we're saying is there exists at least one specific thing. So it defaults to a specific thing. And then if it's inside the scope of a universal, then we're talking about it's a generic thing. Yeah? OK. I saw one more hand. Yeah?
Can you just go over again what the last two are?
Yeah. So let's say these out front. And it's really good to be able to like practice saying these in language. So this says there exists a school, and for all students, there exists some specific school, and for all students, there exists some generic country that they go to school in. This is a weird one because it doesn't make sense of the in predicate, but it's OK. It works out OK. OK, and this one says there's some specific country and some specific school such that all students, everything in the universe that's a student, goes to that school in that country. Okay. Yeah.
Why don't we have an example like this second, where it's like a specific country, but just like generic school in the country?
Oh, I suppose we could do that. I suppose we could do that. So there exists a specific country, Y, CY, and for all students, this one actually makes more like semantic sense, right? There exists a generic. So this one, so this second one is weird. I probably shouldn't have written that down because it's a bizarre sentence. It doesn't make sense of the in. But this one makes more sense. So this one says, there exists some some specific country, and for every student in the world, there's some school in that country that they go to school at. So suppose that every student in the entire world went to a school in Canada. Then this sentence would be true, right? So there's, suppose we'll plug in Canada for that. So there exists at least one country, and it's Canada, such that for anything in the world, if it's a student, then there's at least one random school that they go to in that country. This sentence actually makes much more sense than this sentence, which says there exists some specific school such that for anything in the world, if it's a student, then there's a generic country and they go to school in that. They go to a specific school in that country. They work out to be the same, like, it's not that this is contradictory, it's just weird. This one makes more sense. Yeah. Okay? Yeah.
And then following up on my question last lecture, in an exam, if we had something like this, would you expect us to write all the possibilities, or if we wrote two?
I will make it very clear in the wording of the question whether I expect a symbolization, or if I'm like, if I expect more than one version, I will say this sentence is ambiguous. Please write out at least two different ways it could be read. So I will, and if I don't say that, you are only responsible for writing down one version. It's got to be a right version. It's got to be a reasonable reading of the thing. But unless I say this sentence is ambiguous, give me two versions of it, you're only responsible for one. Yeah, a good question, and I will be very clear about what I'm asking you to do. I'll try, like for the ones that aren't, hey, this sentence is ambiguous, please tell me, I'll try to give you what's called the scope indicators. Remember we talked about that last time? So if I said, if this sentence had said every student went to a certain school in a certain country, then there would be no scope ambiguity. It wouldn't be all of these. It would be, I think, this sentence is every student, there's a certain country with a certain school in it such that all of the students go to it, right? So that would be disambiguate the sentence with those scope indicators. Yeah?
So for the second one and the last one, are they equivalent?
Yeah, I think these work out to be logically equivalent. Well, they're equivalent just in the sense of, like, because of the, they're equivalent because of the semantic, or the meaning of is in A is in B. Because you can't have a school in a country where the school is specific but the country is generic. So if we're talking about one specific school, that school is only in one country, right? So in that sense, the meaning of those two things end up being the same. Yeah.
So usually the four versions they are not equivalent, but in this specific case, they are.
If we're symbolizing, so in doing the translation from logic to language, those two are equivalent. But yeah, in logical terms, so when we get to expansions, you'll see that they would not be expanded in the same way. But nonetheless, they turn out to mean the same thing because of what it means for one thing to be in another thing. Yeah?
Can you give an example where you have something generic in something specific?
Yeah, so there's at least one student in this particular classroom. So I'm not saying, so there's in the, of all the students in this class, so there exists at least one student such that of all the students in this class, they're in this room. And that's true because you're all here, you're all, it's not that you're generic, it's that in that sentence you take on a generic role. Yeah, I'm sure you have many unique and interesting qualities and all that. But does that work? Yeah. Yeah.
I think the last one is missing an EZ.
The last one is missing an EZ. Oh yeah, I did CY instead of, that should be EZ. Thank you. Yeah, that should be EZ, not CY. Thank you, thank you. Good. Okay. You good with this? Okay. Okay. So that was scope ambiguity and double scope ambiguity. So now let's move on to derivations. I have good news about derivations in multi-place predicate logic. There's nothing really new to learn. The chapter in the textbook on this is very short. They're like, just do the same thing from single-place predicate logic, the end. That's at least mildly misleading, because it's not like having learned single-place predicate logic, you can just immediately do these derivations. You do have to practice them, because there are some different moves that you might have to make. It's a skill-building exercise, but there's no technical stuff to learn, which is nice. So really, all the time we're going to spend for doing this stuff is just doing a bunch of examples. Really, we just got a bunch of examples to do. Quickly, before I get on to the examples, there's one thing that I want to flag for you, which is operators. So the first 10 or so examples of multi-place derivations in Logic 2010 have these things in them, and I just want to show you them and explain what they are in order to set them aside, because we're not doing this. We're not going to deal with operators. There's none of this on the exam. I have not assigned you any derivations that involve operators. They're fairly straightforward, but I just want to explain what they are, because it'll be weird, it'll be syntactically weird for you if you see these things. Okay, so an operator is like a name, it's like a variable name. So it's, if I wanted to say David is older than the brother of Alfred, I could write it like this. So Alfred is a name, it's a zero place thing. B1 is the brother of A. So B acts like a subject. It's not a predicate. It acts like a subject in the sentence. And it takes a value. So the brother of Alfred, whoever Alfred's brother is, gets plugged into. So B bracket A says the brother of Alfred. Whoever Alfred's brother is the subject of that. Alfred's brother gets plugged in there. So David is older than the brother of Alfred. We have D in relation to B A. Yeah?
Would it make more sense if you put a bracket on BA rather than just A?
Well, maybe, but BA, then it's like it's a two-place predicate rather than an operator. I don't know. It's a legitimate. If we were designing logic from scratch, I would take that as a very serious proposal, and I'd think hard about it. But given that we're just sort of being handed this syntax, and furthermore that we're not actually going to do this in the class, I propose to just sort of let it slide. So if you see these things it's good to know so that you know a little bit more logic. And if you see these things where it's like there's a predicate, and then within the predicate there's more brackets, I'm like, what's going on there? Nobody told me about this. That's what it is. It's an operator. And if you want to learn about these, there's a lovely section in chapter 5, which is past where we are in the textbook. You can learn all about operators. Okay? Yeah. Do not worry, we're not doing this. We're not doing this. So I'm telling you about this so that if you see it in Logic 2010, you're not like feeling out to lunch or like, hey, they didn't tell me about these brackets within brackets in predicates deal. I'm telling you about it. Don't worry about it. It's not on the exam. We're not doing it in symbolization or derivations or anything like that. Okay? Okay. It's that time of year when people start thinking, oh my God, did I learn this? I can't remember. This is why I'm just trying to like keep you from, I'm trying to avoid this feeling of panic. Okay. If that's good enough for that, it should be good enough because you don't have to do anything about that. Just ignore things with operators. If you see examples with operators in them, you can probably figure out how to solve them. It's not that hard, but don't bother trying if you don't feel like it. Okay, let's do examples. Examples of multiplace derivations. Right. Where are we here? Oh yeah, I was going to do a bunch of different ones. I lost track of, yeah, there we go. Okay. So like I said, there's no new rules to learn. All of the rules that you had from single place derivations or single place predicate logic all just apply here. We can just go ahead and use our old skills. So, show that there exists something such that it's f(ax), and there exists a y such that it's f(xy). Okay. Just a note, in Logic 2010, this one has quantifier negation disabled because they want you to solve it without quantifier negation. So that's the way I'm going to proceed with this. It actually turned out to be easier. I tried this with quantifier negation enabled, and it actually turned out to be harder to solve this thing. So easier to just deal with it, just do it as, I mean, we can just do the regular, you can do an assume ID. I won't bother because I'm going to tell you now it's not going to help. The strategy that we're going to pursue here is just to try to build this thing. So remember from our basic rules derivation in single place, you can, in a derived rules derivation, you always do the assume ID and quantifier negate and try to build a contradiction. Here, our strategy is just going to be to try to build an instance of this thing and then existentially generalize to get it. So what do we need? Let's make some notes just on the side. What do we need to be able to existentially generalize to this thing? Well, we need something such that it's f and then a something, call it phi, and there exists a y such that f, it's got to be the same thing, phi y. Is that phi? Yeah, okay, thank you. I would be embarrassed if I had called it something wrong. All right, so we need some version of that thing, right? We need f a something, and there exists a y such that f something y. And we're just going to try to build those up independently. Put them together, existentially generalize, we'll have our conclusion. Okay, so what do we got and what can we do with it? Well, premise 2 is nice. Premise 2 we can do something with. We can existentially instantiate, right? So let's do that right away. We're always going to existentially instantiate as soon as we can. And we're always going to existentially instantiate to something fresh. So F-A-I. That's premise 2, EI. OK. Cool. So we've got F-A-I. And we can actually existentially generalize that, right? We can say there exists a y such that f a y. Oh, I did not need to do that bracket. There exists a y such that f a y. That's line 2, EG. And that gives us this half of it, right? This is the thing that I was trying to, look, I'm going to try to put this thing together with this thing. And now I've got, there exists a y such that f something y. And our something, we were unclear what it was going to be, but now let's call it a. Actually, did I ever use, I'm not sure if I used that line. All right. Yeah.
Is A being treated as a name letter here?
A name letter, yeah. A to H are always names. They won't be bound to a quantifier, and they can't be like switched up. Okay. Okay. So I'm hoping that there exists a y such that fay is going to fill in this role. We'll see if I can get, what I need to do then to make that work is basically get phi to be a. So if I can get faa, I'm gold, because then I can just existentially generalize this a to x. Let's see if it works. Let's see if I figure out something else. OK, so premise 1 now. Let's deal with this. So we've got for all x, for all y, fxy, then fyx. Cool. So let's universally instantiate it. And you have to start from the outside, right? Because this is the main operator of the sentence. You can't existentially instantiate y yet. You have to peel away this outside universal. So let's existentially instantiate x to, I don't know, a. Because we've got an a in play here. That's fine. So we've got for all y, if f ay, then f y a. And that's just premise 1, ui. So far, so good. And let's existentially instantiate this thing again, because you can't really do all that much with the universal except existentially instantiate it, right? So let's existentially instantiate, because we've got fai here, that could be useful. So let's existentially instantiate this y to I and see what we get. We get fai, then ia. That's line 4, UI. OK? That's a useful line because we're looking to build fa something, and now we're able to get from fai, we're able to get fia. So if we built this in the wrong order, we can just flip it around. Let's try it. So we got on line 2, we got fai. Line 5, we got if fai, then this thing. So let's do it modus ponens. FIA. Line 2, line 5, modus ponens. OK. Yeah.
If you're trying to get 3, can't you do PR2AB?
To get 3. Yes, I suppose you could. Yes, I suppose you could.
So is it a little bit of a silly move in that case?
Well, depends if we're doing a basic rule derivation or a derived rules derivation. Yeah. So if this was a derived rules derivation, we could have gotten 3 in 1 fewer lines. Yeah. Yeah. OK. OK, so what do we got here? What do we got here? And remember, this is our goal. We're trying to get this thing. So fa something, and there exists a y such that f something y. So we've got fai, so that might plug in here. And we've got we've got fia. So maybe we just want to existentially generalize this thing, fia, to exists a y such that fiy. That's line 6, e.g. So we've got, now it turns out, I thought phi was going to be a, but maybe it'll be better if we make phi into I. So we've changed goals halfway through. Because now it looks like it's going to be easier. Since I've got fai, fa something, and there exists a y such that f something y, there exists a y such that f iy. If I use I as my goal, then I can just say, I'm going to put those two lines together, fai, and there exists a y such that fiy, that's line 2, line 7, a join. Now I've done it. I can just existentially generalize all of the i's to x's, fax, sorry. There exists an x such that fax, and there exists a y such that xy. That's line 8, e.g. So I existentially generalize the i's to x's, and you do it in this sentence and also in this sentence. So this I is not bound to anything. It also gets existentially generalized. And that's it. That's the thing that we're looking for. So line 9, direct derivation. OK, so I started off thinking I was going to, so I knew that I had to build this thing, right? Because I'm doing this basic rules. I can't use quantifier negation. I knew I was going to try to build f(a) something, because this x is bound to this quantifier, and there exists a y such that f something y, right? f(a) something, and there exists a y such that f something y. I thought I was going to make a my something, because maybe I could get faa. But as it turns out, I is a better thing to build this out of. Got it. OK. As you can see, it's the same basic rules that you're used to, but you might have to make slightly different moves to get through it. Yeah? Questions? Yeah.
So when you were existentially generalizing line 6 to line 7,
Yeah.
it's OK to change the name variable to a regular variable, but not the same case if you're instantiating something.
OK, so it's OK. When you're existentially generalizing, it's perfectly OK to change a name variable to a variable, or like a name to a variable. So you're saying James is wearing a hat. It's perfectly OK to say there exists something such that it's wearing a hat. So that's what happened. That's the move of existential generalization. If you're existentially instantiating, you still do it to a variable, but it's a variable that has to be totally fresh that we don't know anything about. We say, if you have there exists something that's wearing a hat, you can go from that, you can existentially instantiate to say, there's some I such that I is wearing a hat. Let's call it Ian. Not knowing who Ian is or having any information about Ian, just that Ian's wearing a hat. So EI goes to a variable, but it goes to a totally fresh variable that we know nothing about. Yeah?
So in premise 2, you kept the A.
That's right. That's right. So when you're existentially instantiating, you only do it to the variable that's bound to the quantifier. Yeah? Good. Good. If you're existentially generalizing, so if I have, for example, if I had FAA, I'm allowed to existentially generalize that to FXA or FAX or FXX. Any of those would be fine. Yeah? OK. Yeah?
I guess the thing that's confusing me is you have two separate statements there that are in a conjunction. So should you show it in two steps if you're doing existential generalization, or can you just do it and have it affect both of the things in the conjunction?
Well, so you mean the line from 8 to 9? Yeah. So we're existentially generalizing. This whole thing on line 8 is one big sentence. If we're doing this in official notation, there'd be brackets around it. The whole thing is one big sentence, and you're just existentially generalizing the whole sentence. And when you're existentially generalizing, you generalize to all instances of a variable, even if they're inside the scope of another quantifier. So even though I is inside the scope of this y, Because I is not bound to the y, we replace it as well. Good, good. So we're going to show that B does not stand in the G relation to itself. I'm going to go ahead and assume ID here. Assume ID. Okay. Yeah. Yes, there should be brackets on those B's. Thank you. Yeah. Yeah. Multi-place predicates should always get brackets. That's right. Okay. Now what? This one's not that hard. There's not that many lines to get through it. I mean, if you can get through it. All right. Well, FBA, not really doing. So premise 2 is not really going to do much for us right now. Can't really do anything. Given all we've got so far is GBB, FBA, that's nothing, right? So we've got premise 1, which could be something. We could universally instantiate that to something, see what happens. Given that we've got FBA, and the universal is if X something A, then blah, 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 seems like instantiating it to B is going to be the bet. Like we could universally instantiate premise 1 to A, X, B. All of those are like things that you wouldn't be wildly off base if you took a shot at any of those things. But I'm going to, having worked this out at home, so I'm not so embarrassed in front of you, know how this ends. I'm going to universally instantiate this to B. So, and that's nice because it gives us FBA, then this thing, and we've got FBA, so maybe that'll help. FBA, so I'm going to replace all the examples of X with B's, right? FBA, then if G, BB, if and only if, not G, BB, 2. And that's premise 1, UI. OK. And given that we've got FBA and we've got this big conditional, we'll just do a modus ponens on this thing. So we've got G, BB, if and only if, not G, BB. That is premise 2, sorry, premise 1, premise 2 and line 3 modus ponens. OK. So GBB, if and only if, not GBB. Well, that should strike you as a funny sort of line to have, right? That's a contradiction. That line cannot be true. How did we derive a contradiction? Well, we assumed ID. We assumed the opposite of the thing we're trying to show, and now we've got this line that's clearly contradictory. And to close off this proof, all we have to do is pull the contradiction out of it. So it's a biconditional. Let's pull out 1/2 of it. So we'll say GBB, then not GBB. That is 4 biconditional to conditional. We'll do modus ponens on this thing. So line 2 and line 5, modus ponens, giving us not GBB. Cool. And now we're done. You can either say line 6 direct derivation, or you could have said line 2, line 6 indirect derivation. Either one of those is fine. Box and cancel. Yeah?
I don't understand how we got line 4 to the GBB biconditional.
Well, so that's, OK, so we got line 4. Line 4 is this thing, the consequent of line 3. And we got line 3 by universally instantiating premise 1 to B. And then doing, yeah.
Well, you said premise 2 and
Oh. Wait. We got line 3 by universal instantiating premise 1. Yeah. To B.
Oh,
Yeah? Yeah.
So you're allowed to universally instantiate the x to a b or an a, even though those name variables already occur in your premise.
Absolutely. The universal says you can instantiate it to anything. So the universal is only true if it's true of everything in the universe.
So what was the no capturing rule?
So no capturing says, just remind you, this is good stuff to be reminded of. No capturing says, if I've got for all x, if fx, then there exists a y such that gy and hy, for example. What I'm not allowed to do is universally instantiate this x to y, because that would tell you that it's the same thing as this thing. So that's the no capturing thing. It only applies when you can't universally instantiate this to something that already is bound to a quantifier inside the scope of the thing that's the restriction. Yeah. Yeah.
Isn't it a restriction on how we can only use letter I to Z?
Sorry, yes. Well, no, to universally instantiate? No, you can universally instantiate to anything. So keep in mind, it's good to keep in mind what the universal means. So if I say for all x, fx, what I'm saying is whatever the property f is, it applies to every object in the universe. So it applies to me, it applies to you, it applies to any subset of those things. So the universal, you're allowed to plug anything in so long as you're not helping yourself to too much by doing this capturing thing. Yeah? So letter names, variable names, anything you want. More questions about this? How does this feel to you? Is the multiplace, does it feel like a big step up in difficulty, or so far it's okay? Okay, good, good. It's more taxing on your working memory. So if you're one of these people who are like me, that the real bottleneck for me in doing this stuff is just working memory, just remembering what I was supposed to be doing. And if you've got good working memory, maybe this is trivially easy for you. It took me a bunch more practice to get back in the groove of doing this stuff even after having done single place derivations. Okay, let's do another then. Let's do another. Okay. And we'll do these one all rules. We'll do quantifier negation and all that stuff. So, as always, show the conclusion such that all y, if fy, then gxy. Okay. We're going to assume ID. So it's not the case that there exists an x such that for all y, this thing, gxy, bracket, bracket. Let's assume ID. And then we'll do a standard move should be, if you're in an all rules derivation, a standard move should be you start with an existential, start with anything, you assume ID, and then quantifier negate. So quantifier negation of this is for all x. It's not the case that for all y, fy, then gxy. That's line 2, qn. Okay. Got our basic show line set up. We've done our assume ID. We've done our quantifier negate. All right, now we look around and wonder what we've got and where we're going. So we've got one premise, and we've got one universal on line 3 that are potentially useful. So far, it's unclear what we should be. So we're going to universally instantiate. We've got two things that are potentially useful. and they're both universals. So we're going to universally instantiate to something, but we don't have anything to match yet. So remember the rule from single place where first you existentially instantiate and then you UI to match? Well, we don't have anything, we haven't existentially instantiated anything yet. So we're just going to start universally instantiating to kind of whatever and then try to find something to match that. So fine, all right. Well, I'm going to universally instantiate line 3. I'm just going to do it to x. So UI on line 3 gives us for all y, if fx, then g xy. That's line 3 UI. And I just replaced all the x's with x's there, right? What's the one thing of, so I can universally instantiate line 3 to anything I want, except for one thing. What's the one thing I'm not allowed to universally instantiate to? Y, because that would be capturing. Yeah?
Shouldn't it be Fy, not Fx? That was applied for?
Yes.
So it should be
Yes. Thank you. I think I should use a skinnier pen, because I can't read what I'm writing here. Okay. So, Fy. Okay, we'll universally instantiate that to, it's not the case that for all y, Fy, then g xy. Okay. 3 ui. Okay. Okay. So that's something. We got something now. We got line 4, a new resource available, a negated universal. Well, you can't really do much with a negation of anything except turn it into something more useful. So let's turn this thing into something more useful by doing quantifier negation on it. Yeah? So quantifier negate that, flip the universal to an existential and move the negation inside. Fy, then g xy. So that's line 4, quantifier negate. And now we've got an existential, which we can existentially instantiate to something. What are we going to existentially instantiate it to what are we going to existentially instantiate to? Well, you don't really get a choice about that. It's just whatever's something fresh, something you haven't seen before in the proof. So you don't have to think hard about what to existentially instantiate to, just something fresh, something you don't know anything about. So line 5, EI, will give us, it's not the case that Fi, that's my standard go-to fresh variable, gxi. Remember to replace all of the instances of the variable with the thing you're instantiating to. So this y and this y. Okay. Okay, now we got some stuff. Once again, we have a negated thing, so that's not awesome, but we can turn that into something useful by saying line 6, negation of conditional. So that's Fi and not gxi. Did I do that right? I can never remember negation of conditional. Okay. Okay. Hey, now we got some stuff. Now we got some stuff. Yeah.
universally instantiate the first one to I.
Good. Good. That's what I would do. Yeah. So now we've existentially instantiated to something. We've got it free. Now we're going to UI to match that thing that we existentially instantiated to. So now UI this to I, so premise 1 UI, and that gives us Fi biconditional for all y, g, I, y. Good. And given that I've got Fi, so this is a biconditional with Fi, and I've got Fi on line 7, that looks pretty hopeful. So now I'm going to pull this apart into my conditional to get for all y, g, iy. I'm using more brackets than strictly necessary, but that's fine. Biconditional to conditional. And then on line 7, I'm going to simplify to get the antecedent, simplify this off of line 7, and then line 9, modus ponens, giving me, for all y, I'll write it without the superfluous brackets this time. GIY. Yeah, now that's going to be useful, right? A lovely universal generalization. Okay. Now, what? Well, we EI'd to I, and then we UI'd premise 1 to I to match it, and we got some useful stuff out of it. Is there anything else that we can UI to I that potentially give us more useful stuff? Because currently I don't see how to build a, like, we're in an assume ID, we're in an indirect derivation. Probably the strategy here is going to be to just build a contradiction somehow. I don't see right now how to build a contradiction, but we haven't tapped all of our available resources yet. So we UI'd premise 1 to match I. We could still UI, for example, line 3 to I. See if that does something for us. Let's try it. So line 3, we're going to UI. So that gives us, we're going to replace all the instances of x's with i's. So it's not the case that for all y, fy, then giy. Yeah? Replacing all and only the instances of x with i's. Once again, we've got a negated universal, so the move to make is quantifier negation. So we've got, there exists a y such that it's not the case that fy, then giy. And anytime you get a fresh existential statement, you should probably universally instantiate it to something. Whatever you do, don't universally instantiate to I again. That's verboten. That's bad. We're just going to universally instantiate it to yet another fresh variable. So j, for example. So line 12, we're going to existentially instantiate this to j. So it's not the case that if fj, then g, don't need that bracket, gij. Bracket. All right, we'll do negation of conditional that. Fj and not gij. Ij. Wow. Ij. Okay. Okay. Yeah. You got it. You got it. So we've now got the materials to build our contradiction. We've got what we need to build our contradiction because we've got, so let's do this just carefully one step at a time. Simplify off not gij, 14 simplify. And then we can get the contradiction of this by saying for all y, gij, so we'll say 10 ui. We're going to ui it to j, giving us gij. Ta-da! 15, 16, ID. Yep. Questions? Good. Shall we do another? All right, what do we got here? Oof, all right. One of these big, I'll just remind you, don't succumb to math panic, whatever you do. Don't just look at the whole thing and go, oh, that's too many things, I can't cope with it. Just take it one little step at a time. Yeah?
When you have for all y, giy, can you use AV to change the I variable? I guess not.
So where? Here? Yeah, no, you're absolutely not allowed to do that. Yeah, so the question was on line 10, can we use AV to change the I? And that's specifically what you're not allowed to do. You're allowed to change the Y, but not the I. You're only allowed, the AV changes everything that's bound to the quantifier, not anything that's just sort of in the thing. Okay, good. AV is not really that useful a rule, to be honest. Like, it seems like it should be useful all over the place, but it's typically not, because if you have a universal, you can make it whatever you want. The variable doesn't help or hurt you. Okay, anyway. So, let's show a thing. Let's show this thing. There exists an x such that gx and fx and there exists a y such that fy and hyx. Whoa. How about we write x's and y's differently, Corey? Let's try that. Bracket, bracket. Okay. And we'll assume ID on this thing. Not the case, in order that we can do our nice quantifier negation. So gx and fx and this is a y such that fy and hyx. X's and y's are different. Okay. And then quantifier negate. Flip the quantifiers, move the negation inside. To Qn. Okay. So much for our totally, completely automatic moves. Let's look if there are some like really obvious moves that we should do right away. Well, what do we got? We got a universal in line 3. Premise 1, we have an existential. So probably you're going to want to existentially instantiate right away. Premise 2, we have another big universal. And we don't yet know what we want that to be, so hang on to that for a second. So now our standard rule of first EI and then UI to match. We got one existential and two universals, so we do the existential first to a fresh variable. So premise 1, EI to I. Sorry. Premise 1, EI. Okay. Okay, so now we've EI'd to I, and the game is going to be to UI to match that I. Well, premise 2 is looking pretty hopeful, because if I have F something, then I get whatever this is, so cool. So let's UI that to I, giving us, if Fi, then exists a Y, GY, and FY, and HXY. 2 brackets is enough? Yeah, 2 brackets is enough. So that's premise 2, UI. And we got the antecedent of this thing, so why not modus ponens it? GY and FY and HXY. I drew the brackets wrong on this H. Can we just accept that that's okay? Okay, yeah.
Should that be HIY instead of XY?
Yes, it should. Yes, it should. Thank you. This is my opportunity to also fix the H. H. Because that's an instance of H. Wait. So premise 2, EI, we EI'd that, or UI'd that to XIY. Good. That should be IY as well. Okay. So that's line 4, 5, modus ponens. Did I see another hand? Was that also somebody helping me? Okay, good, good. Thank you. Okay. Once again, we've got an existential. The thing to do is always right away existentially instantiate to something fresh. So let's do that. So we're going to replace all the y's. We're going to replace all the y's, everybody. Don't forget to do all of the things under the scope of the quantifier. That would be foolish if you forgot to do one. It'd be very embarrassing for you. Okay, so line 6, we're going to EI all of the instances of y. So G to J, let's say J. Fj and HI. ij. Okay. So that's fun. We got a bunch of things. We got a string of conjunctions. We got gj and fj and hij. Cool. Now what? Well, yeah, I see a hand. Yeah. Yeah. UI line 3. Yeah, why not? Yeah. Do you want to UI it to, so we got a couple options here. We could UI it to I. Did we do that already? Or we could UI it to J. So now would be a good time to sort of like, let's do some strategy here. Let's do some strategy. So for example, we've got hij. That's a resource that we've got to work with. hij, maybe that could be useful. And we've got here, it's not the case that all this stuff. So if we could somehow get out of that hij, or it's not the case that, so it's not the case that fj, maybe that could be helpful. Yeah?
I think you want to do I first because you're going to, like, once you split up the conjunction, you're going to get, like, you're going to do negation of conditionals, and you're going to get, like, g of x and f of x and not e of x, or, like, x essential y, and then all of that. And then you probably negation of conditional that one, and then it'll be n universe, then you make that one a j, and then negation.
Okay, let's try it. Let's try it. Let's see what happens. So we're going to universally instantiate line 3 because, I mean, you can UI as many times as you want. It doesn't use it up, so we can do both and nothing bad happens. So we're going to replace all the instances of x with I. Gi and fi, and there exists a y such that fy and hyi. Cool. Okay. All right. We're going to have to De Morgan's this thing. Yeah? Aren't we? Yes. Yes, we are. So because this is written in informal notation, we haven't got the brackets. Exactly how this is going to be De Morgan's is a little unclear, but nonetheless, it doesn't matter. What we know is that it doesn't matter. So we're going to have, let's De Morgan's this to, it's not the case that gi and fi, or it's not the case that there exists a y such that fy and hyi. That's line 8, De Morgan's. Now what? Okay, yeah. So if we're like, now I don't know what to do and this isn't going well, don't panic. You can still do it again to J and nothing is lost. You still got these 8 and 9 are still available lines. If they turn out to be useful later, great. If not, that's fine too. You don't lose any marks for doing useless moves. So let's try it. Let's do universally instantiate line 3 again to J. So replacing all instances of x with j, so gj and fj, and there exists a y such that fy and hyj. Bracket, bracket, bracket. Okay. Yeah.
I think after line 7 you're done.
How's that?
Hij,
Uh-huh.
and then fi. So that's there exists a y such that fi and hij, j.
Okay, so we got line 4. So hang on. Say again.
Take that H with ij.
Okay, let's do this one step at a time. So H, I, J, that's line 6, simplify. Yeah?
Yeah, and then you combine that with the fi.
Okay, so Fi
Yeah.
and Hj, Hij?
Yeah. So you
That's-
there exists a y such that f of y and h of y j.
So we're going to existentially generalize from that?
Yeah.
So there exists a y such that Fy and Hyj, that's line 12, existentially generalize. So far, so good. Now what?
And then you take gj and fj from line 7.
Gj and Fj, so Gj and Fj, so that's line 7, simplify.
And you combine it with line 13 and then you're done.
And you can existentially generalize. Very good. Very good. Good. So we got Gj and Fj, and there exists a y such that Fy and Hyj, bracket, bracket, and then we say, so that's line 13 and 14 adjoin. And now we're going to say line 15, existentially generalize, and we're going to switch all the j's to x's. There exists an x. Oh, that is clearly a y. Exists an x such that gx and fx and there exists a y such that fy and hyx. Neat. That's not how I solved it, but that's a perfectly good way of solving it. That's very good. And that's a direct derivation. Line 16, direct derivation. Very good. So I was going to go, the way I had it done was I was going to build a contradiction. Because I looked at that conclusion, I thought, oh, what a pain in the butt. I don't want to have to try to build that up. What a confusing, this is testing my working memory and I don't like it. So what I'm going to do is just build myself a contradiction somehow. I'm just going to keep messing around with things until I get a contradiction. But this gentleman has got good working memory, apparently, and is able to see from the parts that we had how you're going to build the conclusion directly. So we built it through existential generalization. Excellent. Is it clear how that went? No, that was very good. That was very good. And of course, box and cancel, because that's our sort of quasi-religious ritual. Yeah?
Can we do it your way? Because I have an average working.
Okay, yeah, okay, good. Yeah, let's do that. Let's do that. Okay, so actually, quickly, before I erase this, any questions about how we got here? I mean, you can check the video later if you're wondering. Okay, so how far did we get? So I'm going to erase this much, I think. Okay. Oh yeah, we got as far as doing the J's. I'm hearing little distress noises. It's all going to be on YouTube. If you want to look at it at great length, it's all on YouTube. Okay. Okay. So now we're going to go through it the like step-by-step way. You can kind of, it's sometimes called a brute force method, where you're just breaking things down into their components using De Morgan's and negation of conditional, and just trying to generate yourself a contradiction. And that's how I do it. So. Okay, so we're going to De Morgan's line 10 to try to get to the parts of it. So we're going to De Morgan's line 10, and that'll give us. It's not the case that. Oh yeah, no, we were going to do this to J, weren't we? Oh yeah, we did it to J. These are supposed to be J's, aren't they? Yeah. Yes, I just deleted the J part of the J. Okay. Okay, so we're going to De Morgan's line 10. And that'll give us, it's not the case that GJ and FJ, or it's not the case that there exists a Y such that FY and HYJ. Is that right? I think that's right. Yeah. Yeah. Okay. So I'm going to grab this HIJ here. So HIJ, that is line 7, simplify. And then I'm going to put it together with line 4. So we've got on line 4, we've got FI and HIJ. 4, 12, adjoin. All right. So now we've got, we're going to existentially generalize that to say Y. So there exists a Y such that FY and HYJ, line 13 EG. And that's the reason I did those two moves. So why did I pull out the HIJ and why did I put it together with FI and then existentially generalize it? So I'm trying to get access to, line 11 is useful. We De Morgan's did a part. We need to get even deeper into the parts. So to access 1/2 of a disjunction, you build the negation of 1/2 of it. So I was able to build the negation of this thing by putting together line 12 and line 13 and existentially generalizing. So what we're going to do now is say line 14, double negation, and line 11, MTP, giving us that it's not the case that GJ and FJ. Yeah? Okay. And of course, line 15, we're going to De Morgan's that apart. So not GJ or not FJ. 15 De Morgan's. De Morgan's is so useful. De Morgan's and negation of conditional are how you get into the, like if you've got a big complicated thing, they're how you get into the parts of it. Okay.
You do line 7 simplify left, and you get GJ and FJ. Is that the negation of line 15?
Oh yeah, good, very good. So we'll say line 7, simplify, and I'm just going to simplify, because these brackets are ambiguous, it's not clear which part to simplify, so we'll just say GJ and FJ. I was going to do a slightly more tedious version of that, where I simplified off GJ and then use MTP on 17 to give me not FJ, and then simplify off FJ and do the contradiction, but that works just as well. So now we've got line 15 and line 17 an indirect derivation. Those are perfect, and if it's not obvious, you can draw the brackets around it. Those are perfect contradictories of each other. That's how you close this off without doing the existential generalization. Box and cancel. Ooh, bad line. Very good. Good. Yeah.
I'm confused about like how you're applying the rule simplify to line 7. The reason being is because like, perhaps I don't see the brackets and I don't see which parts belong to which. So
Yeah.
like if I were to simplify left, I could say GJ and then have FJ and HIJ.
Yeah. Yeah.
If I were to simplify right, I can have HIJ
Yeah.
and then have GJ and FJ.
Yeah.
So how does that work? Is that would that be like ambiguity or something?
So it's because it's in informal notation, it is slightly ambiguous. So just do this at the bottom here. So P and Q and R, I mean, you could have put the brackets here, or you could have said P and Q and R. And how the simplify rule applies depends on where those brackets are. But because we're in informal notation, we didn't write the brackets, so it's just not clear. I'll tell you that you can just help yourself to whichever interpretation is handier for you at the moment. Logic 2010 will impose one on you. When you're writing on the exam, just pick the one that makes sense. Now, keep in mind that only ever works if it's a string of conjunctions. That's the only case. You can't simplify. Some of the test ones had people simplifying off like half of a conditional or something like that. Hopefully it's clear that you're not allowed to do that. Simplify only applies to conjunctions, and if you have 3 conjunctions in a row, feel free to simplify off. Go ahead and, like, even if it's the Q in the middle, just simplify it off for yourself, because I know that you can get there. It's late in the semester. I'm feeling less formal than when we started. Okay. Okay. Any other questions about this derivation? We probably got time for one more. Yeah, let's do one more. We'll do a really, okay. 20 or 21, that's the question. If we do 20 quickly, we can get to 21. Let's do it. Okay. This is more like, 21 is a really weird one that I'm not going to put on the test. 20 is more like what you'll see in the test, so it's the priority. So let's do that. All right. Show. Oh, God, why did I make myself write this big, long show line? Jeez, Corey. And Fy then exists a y such that h, xy, and gy, bracket, bracket. All right. And the whole thing we're trying to show is what? A universal. So what we're going to do is assume ID and quantify or negate it. Oh, that means I have to write this whole thing out 2 more times. Jeez. All right.
Could you also do it by showing the instance?
Oh, yeah. Let's do that. Whew. Let's do that. That's much easier. Just for the sake of not writing as much. Yeah, I still have to write most of it. Everything except the quantifier. Let's do that. No, but that is actually how we should. Sorry, that was my mistake. If you're showing a universal, it's a really good bet that the thing you're going to want to show is an instance of it. If it's the whole thing is a universal, then it's really, really likely that showing an instance is the way to go about it. So let's do that. Let's do this properly. Silly of me. If it's a universal, if you write a show line for a universal halfway through a derivation, maybe you'll assume ID. But here we're just going to write show instance. We'll try to show an instance of this thing. So h, xy, and fy. Then this is a much nicer thing to show, actually, because it's a conditional now. And so we can start ourselves a conditional derivation. Remember those? Ah, back in the good old days. Fy, assume for CD. And now all we have to show is the consequent of this thing. There exists a y such that h, xy, and gy. Those are y's. Good. Now we're going to assume ID on this much shorter and easier to write thing. H, X, Y, and GY. That's assume ID. And we're going to quantify or negate it, of course, for all y. It's not the case that h, x, y, and gy. Cool. That is line 5, quantifier negation. Okay. Now what? So, as always, survey your resources. Try to figure out what the thing to do first is. We've got premise 1, which is a universal. We've got line 3, which is an existential, and line 6, which is another universal. So, our rule about what to do first here kicks in. Always existentially instantiate and then UI to match. So we're going to existentially instantiate line 3 to something fresh, whatever fresh variable catches your fancy. So, replacing, of course, all instances of y with I, fi. Good. So we got hxi and fi. A very useful line. I feel good about line 3. It's going to turn out to be useful, I think. Okay. Now, we're going to UI to match. We're going to UI to match this I. So let's just go through. So this one looks promising. So premise 1 UI. We're going to say if fi, then gi. I'm just going to go ahead and make the obvious move here. So 7, simplify, 8, modus ponens, giving us gi. Just so I don't forget. OK. And probably we got one more. Yeah, we got one more universal here. We could instantiate to I. So we'll say line 6 UI. Well, giving us, it's not the case that if h, x, I, and g, I. Good. Is that right? So we got line 6. We're going to replace this y with I, this y with I, and this y with I. Good. So negation of a conjunction. I'm going to De Morgan's it apart. See what that gets us. It's not the case that, no, we don't need that bracket. It's not the case that h, xi, or it's not the case that gi. Good. Since we've got gi here, we can get this not xi. So we say line 9, double negate, line 11, MTP. Oh, I'm kind of going off the end there. 9, dn, 11, MTP, giving us not hxi. OK. We're close now. We're very close. What can you do with not hxi?
I was just going to say you could have just simplified 7 and double negated it and modus one opponent to get not gi and then do it ID between 9 and 12.
Could have done that. Could have done that. The other thing that we can do here is line 7 simplify to get hxi. And now we've got our contradiction. 12, 13, ID. Your way would have worked exactly as well. Yeah, yeah. Box. So, hey, we're back to having proof structure. Look at this. So now we've got a contradiction. We can close off the most recent show line. And that gives us our conditional derivation. So on line 4, we did a conditional derivation. And that means that on line 2, we did a universal derivation. Ta-da! Not so bad, right? Okay. Well, I hope that gives you some sense that you can do these things. It is possible, given the skills that you've got, to deal with these things. It's just a matter of keeping straight what to instantiate to, keeping in mind golden rules like how to set up your show lines, and always existentially instantiate first, universally instantiate to match, that kind of thing. All right? Okay, let's call it a day. Thanks, everyone.